presentation is brought to you by the Electronic Structure Lab at the University of Texas at El Paso. At the UTEP campus, our research group developed the software that can be used for performing the density functional theory calculation and self-interaction collection calculation. This is our group picture of our group. Up here, this is Professor Tuna Barua, and this is Professor Rajendra Zope. They are the PIs of our group. As for the postdocs and graduate student, this is Dr. Luis Basurto, and our past group member, Dr. Carlos Diaz. Down here, the Dr. Bohao Chen, and this is myself. One of our graduate student, Mr. Selim Romero, and we work on the software development of the NRLMOL code, FLOSIC code, and the DFT Southwest code. In this presentation, you will learn how to get started with the FLOSIC code. So I'm going to show you how you can download the FLOSIC code, compile it, and run your initial FLOSIC calculations. Okay, for the code we will be using for this tutorial will be the public release version of the FLOSIC code. So the public release version of the FLOSIC code is hosted on the GitHub for the scientists all over the world, and you can download from this URL. And of course, you can use your web browser to download it, but you can also use the git clone command to download. So this is the command in your terminal to download the code to your local machine. There are the several versions of the FLOSIC code, and the development version of the code, FLOSIC code, is hosted at the UTEP server, and they are available upon request. Those versions of the FLOSIC code contains the features that may not be suitable for the public release or the simply as the testing experimental features. In this tutorial, we will use the public release version of the code dated at the September 2022. And I've also prepared the example sample input for you to run the FLOSIC calculation, and that is located at this GitHub, my personal GitHub repository, under the FLOSIC example. So that's what we are going to use. Okay, one of the first challenge for you is to compile the FLOSIC code to prepare the binary of the software. And once you download the binary file, for the users, there are the two files you may need to look at. The one is the make file. The make file contains the instruction to how to build the binary file for the machines to run. And inside of the make file, there are the three sections of interest for the users. The first one is the compiling option section, and second is the compiler and the compiler flag section, and the last one is the linking option section. We will go back to that later. The second file that is important for the user is the parameter2 file. This file contains the static parameters needed for the compilation. And although there are roughly the 40 parameters in this file, and maybe a little bit intimidating at first, but in typical situation, you may only need to change only few of the parameters, static parameters in the parameter2 files, so it shouldn't be as intimidating as the first look. And whenever you make a change to the parameter2 file, don't forget to perform some make clean every time you do that before recompiling the binary. The public release version of the FLOSIC code, the code depends on the library, BLAS library, LAPACK library, and if you are using the OpenMPI, it's also depend on the MPI library as well. Okay, now let's go over a little bit more detail in the make file. On top of the make file, you can find compiling options section. For the public release version of the code, there are only 3 options. The other version of the code has more. The MPI option tells you if you want to compile your code in the parallel mode using MPI, or you just want a serial binary. The group option tells you if you want to add the second layer of the parallelization. So the first layer of the MPI parallelization is done over the mesh, and by turning on the group calculation option, it adds the second layer, the parallelization over the orbital. So this is a very powerful option if you have an access to the powerful supercomputers and want to take advantage of that computing resources. And the third option here is the atom force. This option is useful if you want to optimize the atomic coordinate and the FOD coordinate simultaneously in the FLOSIC calculation. But since this subroutine related to the atomic force is written serially, unless you want to do the simultaneous optimization, I recommend putting the N for this option. And few lines below, you can find the compiler options. The CC stands for the C compiler, and FC and FFF is where you can specify your choice of the compiler. In this option, the GCC compiler is used for the C compilers, and the MPI F90 compiler is used for the Fortran compiler. And if you go down a little bit further, you can find the compiler option section. The C flags is the compiler option for the C compiler. F flags and L flags are compiler options for the Fortran. Now, depending on your machine setup and what kind of the compiler is available, these options will be different. So that you might need to look up the compiler documentation. And finally, what is relevant for the users is the linking options. The linking option section is located almost at the bottom of the make file, the link indicated with the linking option. So linking option tells you how to combine the compiled subroutine, link them together to make one single binary file. So instruction is specified in here. And again, depending on your machine and compiler setting, you may need to comment out or the comment in appropriate option available in here. So the default option should work for the typical Red Hat Linux setup. And this is how the parameter2 files looks like. It contains the static parameters, roughly the 40 of them. Typically, you only need to change a few of them. This depends on the system size. you want to run the calculation for. The max PTS is related to the number of grid points for the numerical integration, and the max OC is related to the number of occupation array, and NDH is the size of the Hamiltonian matrix, and the max sphere, this is the related to the number of sphere used for the variational mesh. And sometimes you might need to change the max unsim when you are editing your basis set. But those are the typical entry you might need to change. When there is a problem running the calculation because of the static parameter, the software will tells you which parameter you need to change. So at least the software indicate what parameter needs to change. And don't forget, every time you make a change in this file, perform the make clean before recompiling the code. Okay, at this point, let's download the source code from the GitHub and compile the code. But before that, let's take you to the GitHub website where the public release version of the FLOSIC code is hosted. On the first glance, there are some useful information on here as well. Under the code, you can find the PDF, more detailed version of the documentation and tutorial PDF file listed here. And under the discussion, you may find some of the useful discussions here as well. Okay, to download the source code, you go to the public release 2020 repository, check the code, and here click this green box that says code and copy the URL right here. And now you go to your local machine in the terminal, and to download the code, you type git clone and copy and paste the URL for the Git repository. This will copy the source code under your directory. So the public release 2020, this is what is being downloaded here. So inside, you can find that the PDF file I just mentioned. And under the FLOSIC directory, you find the source code. And first thing is, let's take a look at parama2 file. Okay, so these are the list of the static parameters used for this software. And depending on the system you want to run calculation, you may need to adjust the parameter. But for now, let's use the default setting. Now let's take a look at the makefile. There is only one single makefile called makefile.fedora. And going to the top of the makefile. And right now, because I'm on the Mac laptop, let me turn off the parallelization. And then comment out the Fedora Linux section and uncomment the Mac OS X section. And here you find the compiler flag section. I will leave as it is. And if you go down almost close to the bottom, you will find the linking option right here. And I will comment out the Fedora and uncomment the Mac OS machine here. And one last thing, depending on your Python installation, you may need to change the line 239 with Python 3 for some system. Although for the typical Linux installation, you shouldn't need to do this. And after you make the appropriate change in the make file, you can type make -f and specify your make file to start the compilation. So this compilation may take some time. And for the sake of the time being, I'm going to cancel the compilation because I have another directory where I precompiled the binary for this presentation. Okay. Once you successfully compile the code, it will create the binary file called the NRLMOL_exe. So this is the software for the FLOSIC calculation. And let's copy this to somewhere more convenient location. Okay. So that's the how you download and compile the code. Going back to the presentation. The minimum input file needed for the FLOSIC code is as follows. For the DFA calculation, what you need is either the single cluster file or 3 symbol ISIMGen and GRPMAT files. The cluster file contains the exchange correlation functional name, the geometry of your system, and charge and moment of your system as well. Alternatively to cluster, you can also use the symbol file, which contains the geometry and exchange correlation functional, and ISIMGen file that contains the information about the basis set, and GRPMAT file, which contains the symmetry group information. Now, when you start your calculation from the cluster file, it will generate those 3 set of the files automatically. When both cluster file and symbol file exist in the same directory, the symbol file gets the priority. So if you want to run calculation from the cluster file at any point, be sure that you don't have the symbol file in your directory. Additionally, the additional option can be specified in the NRLMOL input.dat. This file contains the many calculation options that may be useful for your need. And those are the files you need to run the DFA calculation. For the SIC calculation, you need additional files. The FRMIDT file. This file will list the coordinate for the Fermi orbital descriptors. The FRMGRP file will contain the symmetry group information for the Fermi orbital descriptors. We will come back to the Fermi orbital descriptors later. When the software finds those 2 files in your directory, the SIC calculation will be turned on. And likewise, when those two files don't exist in your directory, then the SIC calculation is turned off. Alternatively to those two sets of the FRM IDT and FRM GRP file, you could instead use the FRM ORB file. Those are the choices for the exchange correlation functional in the FLOSIC code. Several of the LSTA functionals are available, and several the generalized gradient approximation functionals are available, and 3 of the strongly constrained and appropriately normed scan family of the functionals are available. In most of the time, the functional used often with the FLOSIC calculations are highlighted in the blue. The PADI1 92 parameterized LSTA functional, or the PBE, the GGA functional, the scan meta GGA functional, or the R2 scan, the numerically more stable version of the scan functional. Those 4 functionals are typically used with the FLOSIC calculation. One more comment is that in the UTEP version of the FLOSIC code, the libxc functional library is interface to the libxc functional library is there. So it has more additional option for additional choice for the exchange correlation function out there. Okay. To specify the exchange correlation functional in the FLOSIC code input file, you need to translate to the appropriate string. And you can specify the functional string in the either cluster file or the symbol file. In case of the PW92 LSTA, you use the string as the LDA-PW91 star LDA-PW91. The first half of the string corresponds to the exchange functional, and the latter half of the string corresponds to the correlation functional. Although here it says the PW91, that is not the typo, and this is because it uses the GGA PW91 subroutine to perform the PW92 LT functional. So the functional string looks like this for this case. And in case of the PBE functional, this is the functional string you need to put it in your cluster file or the symbol file. Similarly, for the scan meta GGA, this is your functional string, and R2 scan functional, this is your string. The one thing to note for the scan family of the functional is that you can adjust the mesh setting inside of the NRLMOL underscore input.file, and it is highly recommended to use the mesh setting 1 for the scan and either setting 1 or setting 2 for the R2 scan, such that there are sufficient grid points for those two functionals to converge with respect to the variational mesh. This is how the cluster file look like. This is the example for the water molecule. The first line of the cluster file contains the exchange correlation functional string. This is the PBE as an example. And the second line contains the symmetry group. The norm means there is no symmetry. And the third line contains number of atoms in your system. And line 4 to line 6, those are the coordinate of the water molecules with the atomic number here. The all here indicates that the calculation for these atoms are done at the all electron level. And the number down here is the net charge, and this is the net moment of the system. And the geometry coordinate here is in the Hartley atomic unit, so this is in Bohr and not angstrom. Once you run the FLOSIC calculation, the code will generate the several files. The one of the file is the runs file. So the runs file is useful for specifying the restarting options. And for the typical FLOSIC calculation, there are the 3 numbers that may be important for the users. So this is how the runs file looks like. The first line, first number corresponds to the starting iteration numbers. Usually you use 0 unless you have a reason not to. And second number of the first line indicates the geometry number listed in the symbol file. Unless you are optimizing the nuclear coordinate, this number is typically 1. And the second line, the first number, this is your restarting options. If you are optimizing the FODs, the Fermi orbital descriptor positions, the number here is typically 4. The 4 means you restart from the wave function stored in the WF-out file from the previous calculation. So typically you use number 4 here. And sometimes you may want to restart your calculation from the scratch. And for those situations, you put number 3 to indicate that. So that is the runs file. Once you perform your calculation, the code will generate many files. And at first it might be intimidating to the new users, but it shouldn't be, because there are the new users can focus on looking at those output files. Summary file contains the total energy of the every iteration step, and the e-value file contains the eigenvalues of your calculation. And WF-out contains, this is a binary file where the wave function of your calculation gets stored. And you need this file for the typical optimization calculation. And for the DFA calculation, this is the one that is important to the users. For the SIC calculation, you get extra files, additional files. The FRM-IDT, although I mentioned that this is your input file, but at the end of each SIC calculation, the FRM-IDT file will get updated. So every SIC calculation, FOD coordinates will be updated and stored in updated coordinate will be stored in the FRM-IDT file for the following calculation. The FUNDE.out, the FUNDE stands for the force and energy. This file will contain your total energy, the root sum square of your FOD force, and maximum FOD force for each SIC step. The record file contains the total energy, FOD, your FOD coordinate of that particular calculation, and FOD force for that calculation, for each SIC step. So the information in those two files will be appended for each SIC calculation and get longer and longer as you perform more SIC calculation. Finally, SIC underscore energy file. This file contains the orbital contribution of the SIC energies and a little bit more detail about how the SIC energy contribution is coming from. So those are the important output file for the users. Okay, now I'd like to spend some time for reviewing the self-interaction collection theory and method. Now, in the density functional approximation, ideally your exchange correlation functional should cancel out the self-Hartree energies, ideally. But in reality, many of the functionals doesn't, and that creates the improper cancellation. That's the origin of the self-interaction errors. And the method to correct the self-interaction error is called the self-interaction correction. The self-interaction correction method existed actually for a long time. You can go back to the 70s. So this is the Lindgren articles. So the Lindgren, the Hartree-Slater scheme, the self-interaction correction is removed for the self-exchange case from the DFA energies. And the Lindgren analyzed the self-interaction using the Slater's X-alpha theory. And that was what was being done back in the 70s. This is one of the one-electron self-interaction collections in the earlier days. And in 1980s, it comes to the Purdue-Zanger self-interaction collection method. So to date, this is one of the most popular SIC method used in the community. In Purdue-Zanger SIC method, for each occupied orbital, you subtract the self-Hartree and self-exchange correlation energy from the DFA energy. So what is new here from the Lindgren method is this method, Purdue-Zanger approach, also includes the self-correlation. Now, if you look carefully on those SIC terms, those terms depend on the rho I sigma, the orbital density. This is a little bit problematic because now the theory is orbital dependent. Depending on your choice of the orbital density, you get different SIC energies. So the question is, how do you find the appropriate or the correct orbital density that can be used with the PGSIC? Back then, the approach used was the localization equation approach. The localization equation is characterized by this. This is essentially the localization equation. Sometimes it is also referred to as the Pederson equation. Left-hand side of this equation is the off-diagonal element difference of the Lagrange multiplier matrix element. And by setting to 0, it's telling you to get rid of the off-diagonal element. And if you enforce this condition, your orbital density will be localized. And the orbital obtains this way minimize the Purdue-Zanger SIC energy functional. That's the localization equation approach. Using the local orbital with the PGSIC has the advantages, the one of which is the size extensivity, and also you need it for the invariance of the total energy as well. Now, this was done in 1980s, but you don't see as much application of the PGSIC beyond the atoms or the small sized molecules. And reason for that was solving this localization equation was computationally very expensive to do so. So you don't see the application of the PGSIC as much compared to other DFA method. And few decades later, in 2014, it comes to the Fermi loading orbital implementation of the self-interaction collection. So the FLOSIC stands for the Fermi loading orbital self-interaction collection. So in the FLOSIC approach, what we do is you take the PGSIC energy equation like before, but to deal with the SIC term, you use the Fermi loading orbitals. First, you can obtain the Fermi orbital by the unitary transformation from the constant orbital psi j of sigma. Here, the so-called the Fermi orbital descriptor position A of I is used to transform the constant orbital to the Fermi orbital. This AI is called FOD for short. The Fermi orbital is local orbital, but they are not necessarily orthogonal to each other. So you perform the loading orthogonalization schemes to form the Fermi loading orbitals. And that resulting orbital will be used with this PGSIC equation. Now, the Fermi loading orbital is always a local orbital. So the size extensivity and the invariance of the total energy is guaranteed. Now, another way of comparing the different approach for the PGSIC is how you minimize the PGSIC energy. In case of the localization equation, you are minimizing the energy with respect to the element of a unitary transformation, the lambda ij here. Alternatively, you could also minimize the energy with respect to the constant orbital coefficient. In either of those two cases, you are tuning the n square element, where the n is the number of electrons. For the FLOSIC approach, you are minimizing the energy with respect to the Fermi orbital descriptors positions. The FOD has the XYZ 3 of the 3 times the number of electrons. So you have only 3 n element in comparison to the n square element. So in principle, the FLOSIC method has the computational advantage over the traditional localization equation approach. At the UTEP group, beyond the Pardizanga SIC, we also works on the other SIC method. The one of which is the local SIC method. So this, in the local SIC method, you adjust the amount of self-interaction collection point-wise in space, by using the isoorbital indicator. Because some reason the self-interaction correction is more important than the other. And it turns out that local SIC can predict many properties very accurately. And the next on the list is the SDSIC. So the SDSIC was inspired by the success of the local SIC and intended to generalize the local SIC to the GGA functional to the meta GGA functional by resolving the gauge problem. And the third one is the orbital scaled SIC. So the orbital scaled SIC is not actually new. It was done by the Skucelius group back in 2006, but we have worked on implementing this method into the FLOSIC code. So the one of the development FLOSIC code, those other SIC methods are available. And in future tutorial presentation, I will cover how to use those other SIC method. But for now, in this tutorial, we will focus on running the PGSIC calculation. This is the diagram of FLOSIC code, of what FLOSIC code does during the calculation. What is being used in the public release version of the FLOSIC code is the Jacobi rotation approach, which is outlined right here. So in the Jacobi rotation approach, the users supplies the initial guess for the FODs, and based on that FODs, the Fermi orbitals and the Fermi loading orbitals are constructed, and then the software constructs the proceeds calculating the orbital density and the orbital SIC potential. There, the DFA plus SIC Hamiltonian will be constructed. In the Jacobi rotation approach, you apply the Jacobi rotation to diagonalize this DFA plus SIC Hamiltonian. And this process will be repeated until the self-consistency will be reached. Once the self-consistency reaches, the FOD force get computed, and if FOD force get computed, and the same process will be repeated until the force on the FOD converges. So that is what is being done in the Jacobi rotation approach. But there are other flavor of the FLOSIC code. So to your right is the optimized effective potential OEP approach of the Krieger, Lee, and Iafrate, the KLI method. So the difference between the KLI and the Jacobi rotation approach is the following. So up to the constructing the flows and computing the SIC orbital potential, two approaches are same, but instead of constructing the Hamiltonian matrix, in case of the KLI, you compute those extra ingredients and then expose the SIC effect of the SIC to the Konsham potential. That is what is being done here. The advantage of the KLI is that the effect of the SIC is exposed to the entire the eigenvalue spectra. So the SIC effect is there not only for the occupied orbital but also for the unoccupied orbital as well. The KLI approach is available in one of the UTEP version of the FLOSIC code. In the public release version, again, the Jacobi rotation is being used. Okay, for the users who is running the FLOSIC calculation, the ultimate goal is the following. You want to find the set of the FODs that minimize the total energy. And for that, typically the user starts with the converged Kohn-Sham wave function and supplies the initial guess of the FOD. And based on that initial guess of the FOD, the PGSIC total energy and the orbital potentials are computed, followed by the Hamiltonian. And then the FOD force is computed for updating the FOD. And you repeat the step number 3 to step number 5 until you find the minimum total energies. So the challenge for the users are the following two things. The one is supplying the initial FODs and optimizing the FODs. Okay, now let's go back to the terminal and run a FLOSIC calculation. Okay, so in my GitHub account, I have prepared the FLOSIC example repository where you can, contains the sample FLOSIC calculation input. So copy the URL for this repository and go back to your terminal. Okay. So again, to download the GitHub repository, you type the git clone and paste the URL to do so. So inside of this repository, FLOSIC example, you find the hands-on directory. There are the 1, 2, 3, 4, 5, 6, 7, 8 sample calculation input available here. The FODs under those directories are already optimized. So let's take a look at the neon for now. Okay. So here the input you need to run is the symbol file. This line indicates the exchange correlation functional. This is the example for the PW92 LDA functional. And the line here indicates the coordinate for the neon atom. And the ISIMGen file. This file lists the basis set information for the neon atom. And finally, GRP mat. So in the SIC calculation, the symmetry group for the nuclear coordinate is not working, so you can leave it as the identity matrix here. So those three files are needed for both DFA and SIC calculation. For the SIC calculation, you also need FRMIDT file. This lists the FOD coordinate. So the first number on the top indicate the number of FOD for the up spins, and the second number is the number of FODs for the down spins. Because the neon has the 5 up electron and 5 down electron, you have 5 and 5 here. And the 10 lines followed after, those are the coordinate of the 10 FODs. And for now, let me move the first FOD coordinate by a little bit. And the another file you need for the SIC calculation is FRM-GRP file. So this is the symmetry group information for the FODs. In this example, the identity matrix is used, so there is no symmetry. When you are performing the FOD optimization, I would recommend going into the symbol file and make sure the first line says the SCF only, such that your the nuclear geometry doesn't move. And similarly, inside of the NRLMOL input.dat file, there is a line. You can specify the SCF only option here as well. Okay, so let's try to run this calculation. But first, let me copy my FLOSIC code binary here. And there you have it. So I just performed the one complete SCF cycle. Now let's take a look at some of the output file. Inside of the summary file, this is the total energy for each iteration step. So the ETOT column, this column is the DFA energy only. It doesn't contains the SIC energy contribution. And the column that says the EDFT plus SIC, this column is your total energies. The DFA plus SIC total energies. And it took six iterations to converge. Let's take a look at eValue file. So this is your eValue file. The occupation is indicated on the rightest column. And column here is your eValue for each of the Goncham orbital. Okay. Next file to look at is the funded.out file. So this file contains total energy, the root sum square of your FOD force on the second column, and the largest force on the last column. And finally, let's take a look at SIC underscore energy file. So this file contains the SIC energy contribution from each of the orbital, 10 in total. The details are stored in here. And when the code completes the one SCF cycle, your FRMIDT file will get updated as well. And to perform the FOD optimization, you essentially need to run this calculation over and over again. So let's try to run this several times. Okay, that's the second SCF. That's the third SCF. Fourth SCF. And the fifth SCF, and so on. Now let's take a look at the funded.out file. So the column that corresponds to the total energies. As you perform the optimization process, your total energy starts to going down. And similarly, your force from the iteration number 1 to the fifth SIC step, the forces goes down. And you need to keep repeating this optimizations of the FOD until you find the minimum PZSIC energy. So that is the nutshell of how you perform the calculation. Okay. Now for the rest of the presentation, I want to show you the optimum FOD for some of the simple systems to give you the insight of how those FOD looks like. So this is the example for the neon atom. In case of the neon, you have the one FOD at the center. This corresponds to the 1s electron. And you have the 4 FODs that forms the tetrahedron surrounding to it. And this tetrahedron shape is coming from the hybridization of the 2s, 2p FODs. So roughly there is a connection between the FOD and the classical electron shell structure. This is the argon FODs. For the argon, you have the 1s FOD at the center, and you have the first tetrahedron shape right here for the 2s 2p hybridization, and you have another tetrahedron outside, and this second tetrahedron corresponds to the 3s 3p hybridization. So again, this arrangement of the FOD roughly corresponds to the shell structure. This is the manganese atoms. The one in the pink is for the up FOD, and those in whites are the down FODs. In case of the manganese, you have the 4s electron, or the 4s FODs, the two of them, one for the up and one for the down. And the 4s FODs forms the Mickey Mouse ear like shape like this. And as for the FOD down here, for the up FODs, the 3S, 3P, 3D FOD hybridize to form a sphere-like structure here. This is the example for some of the simple molecules, the sodium chloride. And here, this FODs corresponds to the Na, and the other half corresponds to the Cl atom. And here, the Na donates the one of the FODs to the Cl, such that the Na has the neon-like FOD structure and Cl has the argon-like structure. So this is very analogous to how the Lewis structure of the classical electron works. And the FODs, two FODs here in between the Na and Cl, they are responsible for the covalent bonding. This is the example for the double bond C2H4 molecules. Here, the up FODs and down FODs occupy the same coordinate. But you can see those 4 of the FOD in between the carbon molecules, they correspond to the double bond of the Lewis structure. And the final example is the nitrogen dimer. Again, here you can see 3 up FODs between the nitrogen atoms, and another 3 triangle-shaped FODs for the down FODs. And this represents the triple bond for the nitrogen dimer. Okay. The one of the potential challenge for the new users who will be using the FLOSIC code may be how to generate the initial FODs. So the one way to go is, the first step is you should check out this article by the UCAL. They performed the FLOSIC calculation for the atoms ranging from the lithium atom to krypton atoms, and there in the supplementary material you can find the optimized FODs for those various cases of the atoms, and that gives you some idea about the FODs in atoms. And beyond atoms, for the molecules, there have been a few methods proposed for generating the initial FODs. The one of which was the quick FOD method from the Central Michigan University group, and another method was the Monte Carlo algorithm-based FOD generators. You can also use this to generate initial FODs. But in the recently proposed the density-based iteratively approach, in this article under preparation, this seems to be very promising for the generating the initial FODs. So if you have a problem generating your initial FOD for your system you want to study, I would recommend the contacting and collaborating with the UTEP electronic structure group. And As a note before closing this presentation, once again, the documentation PDF file is available in the GitHub for the public release version of the FLOSIC code. And there you can also find the discussion board that may be useful for some users. And you can also ask questions at the FLOSIC mail server. And that concludes my presentation and brief tutorials. Now you can perform the FLOSIC calculation. Thank you for your attention, and go FLOSIC.